This video is brought to you by mywayteaching.com.
So in this part, we are going to study about the conservation of mechanical energy. Okay. See, for simplicity, we demonstrate this important principle for one-dimensional motion. Suppose you just consider a body undergoes displacement of delta x under the action of a conservative force F. Means when a force F is applied to a body, it goes a displacement of delta x. Okay. Then from work energy theorem, we can write K is equal to, that is the change in kinetic energy is given by f of x into delta x, okay, where delta x is displacement. So if the force is conservative, the potential energy function v of x can be defined such that, if we consider the conservative forces, then we can define the potential energy such that minus of delta v is equal to f of x delta x. Okay, so we can write the above equations. Okay, from the above equations we can write delta k plus delta v. If you add, it yields what? Yes, it yields 0. So that is delta of k plus v is equal to 0. So which means that k plus v, the sum of the kinetic and potential energies of the body, is constant. So over the whole path, that is from xi to xf, okay, we can write it as ki plus v of xi is equal to kf plus v of xf. Okay, the potential and kinetic energy, the sum is constant in the system. This quantity, that is k plus v of x, is called total mechanical energy of the system. Okay, k plus v of x, we call this as total mechanical energy of the system. Okay, individually, the kinetic energy K and the potential energy V of X may vary from point to point, but the sum is constant. Here, only the sum is constant, not the individual energies. Okay, so now let us consider some of the definitions for the conservative force. Okay, definitions for conservative force. See, a force f of x is conservative if it can be derived from a scalar quantity, that is v of x, by the relation which we already studied in the equation, that is the equation that we studied before, gives the relation between the conservative force. So the equation, that is delta V is equal to minus of f of x into delta x. Okay. The three-dimensional generalization requires the use of vector derivative, which is not discussed here. Okay, that is the first definition of conservative force. And the second definition, the work done by the conservative force depends only on the endpoints. So that is W is equal to Kf minus Ki, that is equal to V of Xi minus V of Xf. So it depends only on the endpoints, not on the intermediate points. Okay. And the third definition is the work done by this force in a closed path is zero. Okay, the work done in this, okay, by the system in a closed path, as we just saw, that is K plus Vx, the potential and kinetic energy of the system is constant. Okay, that is Ki plus V of Xi is equal to Kf plus V of Xf, isn't it? So that is zero. The work done in a closed path is zero. So thus the principle of conservation of total mechanical energy can be stated as the total mechanical energy of a system is conserved if the forces doing work on it are conservative. Mechanical energy is conserved only if the forces working on it or doing work on it are conserved. So you just consider one simple diagram here. The conversion of potential energy to kinetic energy for a ball of mass m which is dropped from a height h. So at the height h it will be having full of potential energy. So as it reaches the ground, that potential energy is converted into kinetic energy, isn't it? See, that is the simple example. So the total mechanical energies, that is E naught, EH and E small h of the ball at the indicated heights 0, h and h. Okay, the indicated heights, one is 0, you can see here, and h, the height h and the total height h. Okay, so in all these three cases the total mechanical energy is given by, that is E h is given by mgh. Okay, and eh is given by mgh plus half mvh square. Okay, and the E naught is given by half m vf square. Okay, so the constant force is a special case where it is a dependent force f of x. So the mechanical energy is conserved. So we can write eh is equal to E naught. Okay, the mechanical energy is conserved. So that is nothing but mgh is equal to half vf square, and we can write vf as equal to square root of 2gh. Okay, so the as a result, for a freely falling body, eh is equal to the energy at this height is equal to energy at small h. So the height, so from this equation we can obtain vh square is equal to 2g h minus small h. Okay, and it is the familial result from kinematics. At the height h, the energy is purely potential. Okay, at this height The energy is purely potential and again it is converted to kinetic energy at height small h and fully kinetic energy at ground level. Okay, that is nothing but conservation of mechanical energy. So now let us consider one simple problem. A bob of mass m is suspended by a light string of length L. Okay, now it is suspended by the light string of length L. It is imparted a horizontal velocity v naught. Okay, at the lowest point A. At the lowest point A, such that it completes a semicircular trajectory in the vertical plane with the string becoming slack only on reaching the topmost point C. So obtain an expression for V naught, the speeds at points B and C, and the ratio of the kinetic energies Kb by Kc at B and C, and even comment on the nature of the trajectory of the bob after it reaches the point C. Okay, you can consider this figure. So, coming to the solution part, so there are two external forces on the bob. One is the gravity and the another one is the tension in the string, isn't it? Yes, it is suspended using the string only. So here they have mentioned right TA and here mg. So these two are the forces which are acting on this bob. So the latter does not know work since the displacement of the bob is always normal to the string. Okay. So the potential energy of the bob is thus associated with the gravitational force. The total mechanical energy E of the system is conserved. So we take potential energy of the system to be 0 at the lowest point A. Okay. So we can write at A the energy is given by half mv naught square. Okay, and using Newton's second law, the tension Ta minus mg is equal to m v naught square by L. Okay, this is by using Newton's second law. And here Ta is the tension in the string at A. At the highest point C, the string slackens. As this tension in the string Tc becomes 0, so we can consider at point C now. At this point, E will become half mvc square plus 2mgl. Okay, so again by using Newton's second law, we can write mg is equal to mvc square by L, where Vc is the speed at C. So from the equations that is just now I wrote equation 1 and equation 2. Okay, these two we can get the value of capital E. So that value is given by 5 by 2 mgl. Okay, equating this to the energy at A. Okay, equating this to the energy at A, that is nothing but half mv naught square. Energy at C, that is 5 by 2 mgh, equating to the energy at A, that is half v naught square. So we know that Vc is equal to square root of GL, isn't it? So at B, the energy is given by how much? E is equal to half m Vp square plus mgl. So equating this to the energy at A, and even by considering the result from the first part, that is V naught square is equal to 5gl. So we can equate the equations half m Vp square plus mgl is equal to half m V naught square. Okay, so that is given by 5 by 2 mgl, where Vb, we can get the value of Vb is equal to square root of 3gl. So, and the ratio Kb by Kc, we can get easily half m Vb square by half m Vc square, which is given by 3 by 1. So at point C, the string becomes slack and the velocity of the bob is horizontal and it is to the left. If the connecting string is cut at this instant, the bob will execute a projectile motion with horizontal projection to a rock kicked horizontally from the edge of a cliff. Otherwise, the bob will continue in its circular path and it will complete the revolution. Okay.